All right, this is part 5 of the join stuff inside LS-Dyna. Basically, it's how to set up a cylindrical joint. Cylindrical joint are basically a joint that follows this schematic. Essentially allows translation along the rotation axis, as well as a rotation along the rotation axis. So to do this, we need to define point 1 and 2, which is usually at the center of the cylinders, and point 2 is going to be coincident with point 1. And point 3, which is going to be offset from point 1 along the rotation axis, and point 4 is going to be coincident with point 3. And this basically sets up the basic schematic for a cylindrical joint inside LS-Dyna. Just as with other joints, what we do with this is that we create two CNRBs that's going to be tied to the surfaces, to the nodes of the corresponding cylindrical joint, and the CNRB are going to be tied together through the constraint joint coordinates cylindrical keyword, which is going to generate a kinematic condition, a kinematic relationship between the two CNRBs, which are tied to the node sets that's defined in 9001 and 9002. And the basic relationship graphically look like this. Point 1 and 2 is going to be at the center. Point 3 and 4 is going to be offset from point 1 and 2. Both are coincident, and they're going to be along the rotation axis. And this is basically what allows us to generate a relationship that look like this, where you have a joint that allows the rotation and the translation to happen between the red and blue surfaces, and nothing else. All right, let's look at how to do this as a demo. All right, to do the demo, let's call this the inside piece. Let's call this the outside piece. All right. We'll suppress the contact. We don't need it. And then let's go ahead and create a couple different coordinate systems here. Okay. So the first coordinate system we're gonna create is this piece right here. I'm gonna call this actually, and you can see that's gonna be situated at the center of that coordinate systems. And let's create another coordinate system, which is going to be sitting right there. You can sort of see these two are basically coincident, right? And what we want to do here is that we're going to translate this along the x-axis. So for this one, I'm going to change this to the global coordinate system, and I'm going to call this, say, for example, 5 to -3 or something. Let's do that, yeah. Which is going to put this way over here, right? Sort of, and you can sort of see the reason this point is along the rotation axis of this point is because the rotation axis is defined along the x-axis, and the only coordinate difference between these 2 points are the x-axis, the x-coordinates, which means it's along the rotation axis. And then I'm gonna go ahead and mesh this with a default mesh. Oops, sorry, I didn't mean to do that. I want my units back to the units that I'm more comfortable with. And let's do like something like this. Oh, that's too fine. Sorry. Okay, that's better. All right, just same as last time, right? What we wanted to do with this is that for the inside face, I'm gonna create this call this the inside cylinder. I'm gonna call this the inside cylinder. And I'm gonna call the one I created earlier the outside cylinder. Okay, and then when I convert this one to a nodal selection, and convert this one to a nodal selection, I'm gonna call this inside node set. And I'm gonna call this 9001. I'm gonna call this the inside node set. All right. And same thing as everything else in the previous joint analysis. What I want to do here is I want to do constraint joint COR. I want to call this cylindrical. Okay, and then what we're going to do here, same thing as before. We're going to generate two set of CNRBs. You see the 9001 and 9002 node set from here and here are constrained respectively to 8001 and 8002 CNRB node ID. This CNIB ID of 8001 and 8002 are gonna be tied together through a joint, and the joint is gonna tie them together through 12.7 and 5. 12.7 is the first point, 12.700, right? And the second point is gonna be 500. So the 12.7 and 5 are gonna be tied together, basically just as you see on the screen right here. These 2 points are gonna be tied together through the joint coordinates. The joint coordinates are following these two systems. They are going to be along the x-axis because the only thing that's different is x coordinate, and this allows us to basically tie 8001 and 8002 together through a cylindrical joint, and then 8001 and 8002 are tied to the node sets, which is what allows you to generate a joint between two different node sets on these two bodies. Let's go ahead and set a termination time of some arbitrary value. For something like this, right, we can set a fixed support on the outside, right? We'll set a fixed support on the outside, and then we can tie a remote displacement, say for example, on the little button I have right there, right? I'll tie this on this little button right here, and then I can change this to the coordinate system that's in the center, and make sure it's placed right on that surface, right? And then because I know I can translate along the x-axis, I can set some value along the x-axis, and I can also set some rotation along the axis, which I can do like 45 degrees, for example. And then I'll constrain all the other degree of freedom, set this to rigid. And what this will allows us to do is to generate a joint. Actually, I should probably free these. I don't know. I think about it because the joint is gonna constrain them instead of me having to constrain it in the boundary conditions. Okay. And once you have something like this, the model is basically ready to solve. Usually what you want to do is go ahead and get rid of the default database cards and default control cards because those are usually not helpful. And for something like this, you just want to define your own database and control card. And for something as simple as this, the only thing we really need is a join force interface database and a D3 plot database. And together, they're going to generate the information we need in the basic D3 plot. And once you do that, you're going to have a joint that look like this, right? So this is a rotation, a little bit more than 45 degree in this example, right? But it's like 120 in this example. But basically, it gives you two bodies that are kinematically related to each other through the joints. It allows the translation and the rotation along that joint. And this is how you do a cylindrical joint inside LS-Dyna. Thank you.